Good afternoon. It's my honor to introduce Mr. Matt Mickelson. So Matt is a principal in MITRE's Naval Program Division. Matt has spent 20 years integrating emerging technologies, including cyber, AI, and autonomy, to improve some of the world's largest organizations. He has given invited talks in academia and industry. He was a keynote speaker at last year's IEEE ICTI conference and recently an invited speaker for the National Cybersecurity Alliance at the NASDAQ. As a child, he convinced his parents they needed a color TV. And ever since, he has had a passion for identifying and developing disruptive technology. Now he actively coordinates advanced research programs in cybersecurity at the Office of Naval Research. With further ado, let's welcome Matt.
Thank you. I'm here to talk about physics rules, physics-based approach for creating cyber-resilient systems, specifically cyber-physical systems. Let's get started. So a little motivation for why we're here. There have been a spate of news articles highlighting cyber attacks on cyber-physical systems. Won't read these out loud to you, but you've probably seen them in the news, everything from airplanes to industrial control systems to cars to basic IoT in your home. The reason why these are making the news is because these are affecting everybody's lives today, and it's more than hacking these systems is more than just a dump of data, compromised credentials, compromised identities. These things move in the real world. They stand to hurt you or worse. So quick quote about technology change. This is a quote from Douglas Adams, who wrote Hitchhiker's Guide to the Galaxy. If you haven't ever read Hitchhiker's Guide to the Galaxy, I highly recommend it. But basically what he does is he breaks down technology into three basic categories. There's all the stuff that existed before you were born, right? And that's just normal. Then there's all the stuff that comes out between when you're born and when you turn 30. And this is all really interesting, cool stuff. You can make a career out of it. It's really exciting. And then there's everything that comes out after you turn 30, which is the end of civilization as you know it. So what's really changing with all these news articles? Well, the common thread is obviously the cyber-physical systems. These things, like we've already talked about, they move in the real world, right? It's not just about compromising your data. These things can hurt or kill people if things go wrong. And being connected to the network, God forbid, connected to the entire internet across the world, means that they're controllable, hackable. You can push data to these things and actually actuate movement in the real world. What differentiates CPS? I'm going to find out who all the math majors are in a second. There are a couple distinguishing characteristics between IT systems, traditional IT systems that just work with data, and cyber-physical systems. I'll highlight a few of these things. Probably most notably, cyber-physical systems are intended to have a lifespan in terms of decades, where some of the IT systems, your laptop, your phone, typically have a lifespan of anywhere between 1 and 5 years, depending on what they are and how you use it. Cyber-physical systems that operate in an industrial control setting, in a car, on an airplane, those are designed from day one to last for 20, 30, and sometimes, in some cases, 40 or even 50 years. So the lifespan is different. And when you start to think about that in terms of how long those systems are in use, many of them were deployed before cyber was really a thing, right? Much less today's crop of exploits in the cyber world. They were just never designed with any of the cyber exploits in mind. They're also not patched, right? If they're in an operational setting, in the middle of an industrial control system, in the middle of a manufacturing facility, or embedded in a car or an airplane, sometimes they're not touched for years. So the normal Patch Tuesday that you get with Windows and Microsoft does not exist for cyber-physical systems. Some of these things really are not accessible. We've already kind of talked about the health and safety concerns because they move and actuate things in the real world. They also have operational controls. I'll kind of look at the last one. Whereas a server, a web server, an application server is typically run and maintained by an IT professional, someone who has a background in IT. Most of the cyber physical systems are not run by an IT person, much less a security person. They're run by an industrial control operator, right? So we have a lot of different aspects that make cyber for cyber physical systems really interesting and in some cases really dangerous. So the first thing that we need to know about cyber physical systems is what to pay attention to, right? Everything in a cyber physical system really needs to be motivated by the physical part of the system, right? That's the part that can move, that can hurt you, that can kill people, that can cause real damage in the real world. So if you've heard about the confidentiality, integrity, availability triad of cybersecurity, availability is the #1 component for cyber physical systems. What's in this picture is actually a picture of the Per-1 nuclear reactor right here at Purdue. If you're running a nuclear reactor and it's digital, which the one here is, if it's connected in any way, your #1 priority is to make sure it is available and you keep it running, right? Confidentiality is important, but it's of less importance, right? We don't need things like heavyweight encryption because the data in the control loop of most of these cyber physical systems, once it's 2 or 3 seconds old, it's probably not interesting anymore. So we need to remember that the availability is the #1 priority. Okay, so now that we know that availability is the #1 priority, what can we actually do? What is that main physical requirement? If we're going to imbue cyber or we're going to put security constraints on the cyber physical system, we absolutely cannot disrupt that availability, right? If the company that this is going on, or if the company that owns the equipment that is going to be employing the cyber is in business and that cyber physical system is a part of their business, you cannot shut the operation down. It is business critical function. If it's generating electricity for the power grid, if it's driving you down the highway, it doesn't really matter. The #1 priority is still the availability, and we can't disrupt that. It also has to meet the real-time constraints and the deadlines of a real-time system. The nice thing is, we're going to see in a little bit, that the real-time system operates a lot slower than you're used to working with IT systems. So the periodic control loops, which is described in this picture, which is the sensing of the real world by the sensor, the processing, the passing the processed information about the real world to an actuator, and the moving of the actuator forms a control loop. That control loop only moves at the speed at which the external world really starts to evolve, which tends to only be somewhere between 40 and 200 hertz, as opposed to the 2 gigahertz that most of you have in your phones or on a typical system. So one advantage of doing cyber on cyber physical systems is that if we're going to be doing any sort of monitoring and execution and processing, if we're processing at 2 gigahertz and the control loop is only going at 100 hertz, we have a lot of shots for every clock cycle, every loop of that control loop. The periodicity can tolerate occasional disruption, and this is what is actually ultimately going to lead us to greater cyber resilience here in a minute. So why? In short, inertia. Inertia of the cyber physical system, specifically the physical side of that cyber physical system, provides a very natural ability to tolerate small faults, right? If you're driving your car on the interstate, you have about 4,000 pounds of car moving at 60 miles an hour, if you're obeying the speed limit. That's a lot of inertia. If the braking system were to completely disappear for 100 milliseconds, you probably wouldn't even notice, right? So how can we take advantage of the inertia to give us cyber resilience in this cyber physical system? The nice thing is physical laws don't need law enforcement. An attacker, a malicious attacker cannot change the laws of physics. This is something that's completely off limits to the adversary. So it's another really great thing to be able to weave into our system. And we've already talked about the order of magnitude difference between how fast we can sense and respond in a IT system and how fast the control loop of that cyber physical system is actually moving. So now we're on to something, but how do we actually get inertia in the physical laws to translate into actual cyber resiliency in the system? So the first step is to build on what is traditionally in these safety critical systems. Airplanes have multiple engines because if there's mechanical failure on one engine, you could still land the plane. You're not stuck. Safety critical design systems have redundant components for the same reason. So we're going to build on the redundancy that's actually built into many of these safety critical systems. The problem with today's systems that have redundancy in them is that for cyber creates a common mode failure. It's no good to have 4 engines on an airplane if the same cyber attack affects all 4 of them at the same time, right? So that redundancy is great for mechanical failure, but it's really not good against cyber. So the next step is how do we actually extend this redundancy to give us protection in the cyber world? This is the slide that kind of sums up everything about the approach. I'm going to go over it a little bit, but then the rest of the talk I'm going to dive into each one of these in a little bit more detail and cover each one of them independently. So the first thing that we're going to do to get resiliency by design out of this is we're going to provide some artificial diversity. So now it might make sense to kind of come up here and point. So the different colors up here represent software diversity. So if you believe me that we can do some binary and software transformations to make the firmware of these controllers, these 3 controllers that are up here on the screen, functionally equivalent but make them look different. So we can change and randomize the memory layout, we can mess with the stack, we can mess with the heap, we can do a lot of different transformations without changing the functionality of these controllers but making it look different to an attacker. So if an attacker has a malicious message that may compromise one controller, it may not compromise another controller. That's the whole point. The next step is an engineered fast crash. This is going to seem a little counterintuitive. We're going to talk about it a little bit more in detail. Hopefully it makes more sense by the time I'm done. But the faster we can crash, the less the system is down, and the less the system is down, the more we can tolerate that disruption for the physical inertia of the physical system. Controller recovery can help us restore to a known good state. That seems fairly obvious. We'll come back to that one in a little more detail as well. And the delayed input sharing is one of the critical pieces to making this all work as well. So diversity is good. Crashing quickly and recovering quickly is good so that we can absorb the fault. And then the delayed input sharing is going to help us keep one of these controllers clean. So remember, a successful attack, cyber or otherwise, this is a football example, but a successful attack requires 2 things. Not only a crash, you need the target to lose control of whatever it's controlling, but you also need to recover control, right? So if you're the attacker, you need to pick up the ball and maintain control. It's not enough just to crash the system. You have to create the fault, and then you have to establish some sort of foothold or control of that program to take it over. And we're going to use those 2 things in a second. The artificial diversity prevents the common mode failure, which we talked about before. So in this particular case, I've got them color-coded 3 different ways. And this picture is basically just showing a single malicious message and how that might be processed by 3 controllers, all of which are functionally equivalent, but look different in memory, layout, and computation. So the malicious message, which is conveniently coded as a skull and crossbones, will own the top controller, but it will crash controller 1 and controller 2, because in this particular case, the compromise that this piece of code is looking at, the part of controller 1 and controller 2 that it's trying to jump to and execute and regain control isn't where it is in controller 0. It's in a different spot. Things have been moved around. And the most likely, the 99.99% likely outcome of that is a crash. So what we now have is we have the ability to detect when malicious messages are coming to these controllers, but unfortunately we still have 2 machines that have crashed on us. So we're not there yet. But we have prevented the common mode failure. The next thing we need to do is to keep one of these guys clean. So how do we keep one of them clean? We put a delay queue in front of one of them. Without loss of generality, I'm putting it on the bottom. So what we have is a first in, first out message queue of some length. And all that's going to do is that's going to that's going to take all of the stream of inputs, and it's essentially going to keep this guy 100 milliseconds or 200 milliseconds in the past, right? This guy is going to be executing later than C0 and C1, right? Now, if a malicious message comes in that can compromise C0, C1 is going to crash, which we just talked about, but C2 hasn't seen that bad message yet, right? It's trapped in this delay queue somewhere. Okay, so now we can keep one healthy. Now what? Now we want to limit the fault time. So this is the only real math I'm going to include in here. There's a lot of technical details and technical implementation, but I'm going to try to stick to most of the high-level conceptual on this talk. But essentially, that message queue that we just talked about needs to be long enough for us to be able to see a crash happen and notice that the crash has happened while the malicious message was in this message queue here. But it needs to not be so long that we can't tolerate the outage in the inertia of the system. So now we have an upper bound and a lower bound for how long that message queue needs to be. The paradox, which I kind of alluded to at the beginning, is that faster crashes lead to less time that the system is in an uncontrolled state, leads to the ability to absorb that fault in the inertia of the system, which leads to a more resilient system. So if we put all these things together, you could have malicious messages theoretically never getting to C0, and the trade-off is that C0 is living 100, 200 milliseconds later than the other ones, but if we can absorb that fault every time it happens in the inertia of the system, nothing theoretically is ever visible to the user of that operational system. So again, going back to the car example, if this is the braking system and you're driving down the highway, you have the 4,000 pounds of car at 60 miles an hour worth of inertia. Every time something happens, there may be a crash, but one of these controllers is going to stay clean at the expense of being a little bit late, but we can absorb the lateness as the fault in the inertia of the system. So I'll go ahead and stop. Well, I'll stop for a second. Are there any questions so far? Because I know I talk a little bit fast. This is essentially the crux of using inertia and using the physical constructs to imbue these cyber-physical systems with cyber resiliency. So now what? Well, the first thing that somebody does is there's usually some smart guy in the back of the room or smart girl in the back of the room that's like, okay, that's cute, but I'm just going to flood your bus with bad traffic, right? I'm just going to keep you in a crash state the entire time. Okay, well, that's fair. So the first enhancement that we're going to do to the core design is to actually prevent some sort of denial of service to keep that from happening. And the way that we do that is we use some sort of out-of-band memory, right? Short-term memory. It can be as crude and naive as you want. If we have some way to remember what these bad messages are when we see them, we keep them in a short-term memory, and if we ever see them on the bus again, we just drop them, right? So that's the blacklist approach. If we're running this cyber-physical system in a controlled operational environment, and we know that there's only 4 valid messages anytime, we could actually whitelist those messages. So that's the whitelist approach. Usually there's another smart person in the back of the room that says, oh yeah, that's cute, but that's not going to prevent a denial of service. No, it's not actually going to prevent a denial of service, but what it is going to do is it's going to require the attacker to come up with a unique exploit every time, every bus cycle, which makes it exceptionally expensive for an adversary to do. Okay, so what's next? We can actually get diversity through more ways than just that magic software transformation that I was talking about before. We could actually use different hardware, right? So what if we had 3 different controllers from 3 different manufacturers and 3 different vendors? That's even more diversity, right? Because I haven't seen, if these are PLCs, I haven't seen an attack yet that works with one piece of code on Siemens and Allen Bradley simultaneously, right? So you can diversify the software, you can also diversify the hardware. Similarly, if this is an IT system, I haven't seen an attack that works equally well with the same piece of code on x86, ARM, and FPGA, right? So you can play this game all day long. We can also use complementary protection, so long as they're orthogonal, right? So if you're familiar with stack canaries, control flow, address sanitization, memory sanitization, any of these techniques will actually continue to improve the diversity. The more diversity that we have, the more likely we are to keep one of these alive, and the more likely we are to see a crash. I guess this is a third enhancement that we can make, is use an out-of-band simulator. I affectionately refer to this as our, this is our Google Maps in a tunnel scenario. So what happens when you drive through a tunnel with Google Maps? Well, Google Maps doesn't just forget about you. It does assume that you're continuing to move on a straight line and you're probably staying on the road, right? And it will continue to track you, and it will continue to extrapolate your position on the map until it regains a signal again. So yet another thing that we can do, this is actually one of the more nefarious use cases, is what I'll call low, slow sensor drift. So you're not going to actually crash the system. You're going to feed it just slightly off until it's way off at some point in the future. So that's probably the worst possible malicious attack that you could do on some of these. But if you have an out-of-band simulator that's constantly predicting where you should be, and if it ever deviates from where the sensors say that it is, whether or not you had an actual crash, you can now call that situation a crash, and you can call for those controllers to reboot and recover. So this is another way that you can actually recover and prevent and defend against bad and manipulated sensor data. This one adds some runtime overhead. But it's usually pretty negligible because you don't need a full universe simulator to be able to do this. This will work with even just a simple lookup table, right? It's you were here a minute ago. I'm just going to extrapolate a linear extrapolation of where I think you should be right now. Or even just a simple lookup table is enough sometimes to give you an indication of whether or not somebody's been messing with your sensor data. There are also other variants. So what we talked about, what I had up on here a few minutes ago, which is the triply redundant system, is sort of the mathematically minimum set of redundancy that you need to be able to ensure that upon a malicious message that is going to compromise some machine, at least one of them are going to crash, so you'll see this canary, you'll see the crash as the canary, and you'll be able to identify that there has been a malicious event, and you still have a third one that you can keep clean. You can actually do this with 4. So if you are trying to apply this to a system and you open it up and you find out that it has redundant components in it and it has 4 redundant components, that's great. We can still do this. If you can actually do it with 2. It's not as good as with 3, but you can actually put 2 of them in a backup failover situation where with an intermediary, which technically acts as a third system, but with 2 of them and an intermediary, you can identify a crash in one, immediately fail over to the other one, and then when you recover the first one, that one comes up as the backup. So you can be constantly bouncing back and forth in a backup failover situation. The no redundancy one is a little bit of a twist on what we've talked about so far. So I'll talk about this one because it's kind of cool. We identified that you can actually do this without any redundancy in the system at all. And the way it works with no redundancy is you just reboot the controller over and over and over and over and over again. So if you can reboot this controller every 200 milliseconds, and remember, these controllers are not your laptop. They don't take 2 minutes to boot up. There are some tricks that you can do to actually skip the boot up and scan times and things like that. So it is possible to actually reboot these controllers that fast. If you can reboot a controller in 100, 200 milliseconds, that's actually faster than the attacker can write to flash memory, which is kind of cool. And second of all, if you can cache a number of these diversified images for that controller, Every time you reboot that controller, you can come up with a diversified image. So you can get that moving target defense in addition to the rebooting fast enough to prevent persistence on the system. So there is a way to just, through constant rebooting, enable the same results. And the constant rebooting takes advantage of the inertia in the system as well. You're just doing it every time. It's essentially equivalent to every control loop having a malicious message that's going to crash. Let's see, did I leave any out? I think we're good. Okay, so what's next? This is really cool. And right now it works for cyber-physical systems because the cyber-physical systems have that physical side of the system, and the physical side of the system has these things that the attacker and the adversary can't manipulate, namely the laws of physics, specifically inertia. There are some systems that inherit their inertia from other things. So a radar system, whether it's LiDAR, RF radar, it doesn't, the pixels on the screen, the radar system itself doesn't have any inertia. However, the things that it's measuring do, right? So if this is monitoring airplanes, or it's measuring people, pedestrians, cars, whatever it happens to be, those things all have inertia because they're in the real world. And these dots on the screen are going to inherit the inertia of the objects in real life. So while the underlying system doesn't have any inertia, the things that are moving on here do. So we can use the inertia that's essentially inherited from the real world in this system to accomplish the same thing that we could before. So this actually extends to things outside of just purely cyber-physical systems. Next, which sort of abstracts another step further, is there are things with virtual inertia. We've all watched Netflix and we've all watched YouTube, right? Streaming audio and streaming video, while they don't exhibit physical inertia in the real world, if 100 frames of your Netflix video get dropped, again, you don't even notice. Like, there's a blurring effect in your mind. So anything streaming over UDP, anything streaming, period, regardless of the protocol, is going to exhibit some of these features, and we're able to use this as virtual inertia. So these are more future research topics. We really haven't explored these to the same degree that we have with the cyber-physical systems that exhibit real inertia. But we're starting to see the application of this technique on purely IT systems that exhibit these virtual inertia concepts. And I guess I'm talking fast because I'm already telling you to go do something new already. Let's see. Yep. So thank you. This is me. Special thanks to most of the slides in here. Most of this concept was developed through research at the Office of Naval Research, including the titles of these programs and a lot of the future research. If you're interested in this, absolutely let us know. We're looking for great ideas all the time. We're looking for twists on this. Obviously, this was just a high-level conceptual overview of how we can get cyber resiliency out of things that exhibit inertia. But there are other different physical constructs that are off limits to an adversary or an attacker. Anything else that's inherited through the laws of physics works in this construct. We're looking at the next generation of ideas. We're looking at the next generation of tactics and techniques for these types of systems. And with that, I will get off the stage and entertain as many questions as you have because I finished up rather early.
So you gave an example of a brake in a car.
Mm-hmm.
So we know that we could try to attack the brake control unit,
Mm-hmm.
which actually sends messages with a frequency of or with a periodicity of 10 milliseconds. So
Okay.
what is the time limit that you give for the inertia to protect your car from getting damaged when you are actually disabling the brake control unit?
Sure. So every subcomponent of a system is going to be different, and this is where it turns from a research exercise into more of what I would call a systems engineering exercise. Because what works for the braking controller is not necessarily going to work for the flight management system on an airplane, is not necessarily going to work for the control rod on a nuclear reactor. What I can tell you, though, is that it depends. If you remember the slide that I had up there that had the upper bound and the lower bound for the length of the message queue. The length of your message queue needs to be long enough so that you'll actually see the attack happen and you'll capture whatever message caused that fault or the exploit to happen. You want to be able to trap that. It needs to be long enough to trap it in the queue, but it needs to be not so long that the inertia of the system can't absorb it, right? So for the braking system of a car, one, it depends on if the car is moving, but assuming the car is moving and it has some inertia, you have a fair amount of time. I don't have an exact number of milliseconds to tell you. We have done some work on some really fast-moving systems. The system in question is essentially an electromagnetic door lock, which is actually akin to the electromagnetic system that holds the control rods at a nuclear reactor. So if you turn the electromagnet off, the weight will drop away. So the math in question there is how quickly do you need to be able to turn the electromagnet back on so that whatever weight is attached doesn't drop, because once it drops, once it exceeds some threshold, you're never going to pull it back if you turn it on. That tends to be around 15 to 25 milliseconds, and we can still do that. And that basically, we can still accommodate that because it comes back to the fact that the IT systems that we're using to monitor are basically operating on a 2 gigahertz cycle. So for every 200 hertz cycle of the car control loop, we have millions of shots at that clock cycle, right? So we see it many, 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 many times. Does that answer your question?
Yes, somewhat.
Sort of?
Yes.
Okay. So it works on even systems that that can only accommodate like a 10 to 25 millisecond downtime.
Okay.
So, so I am aware of a complex control system where there is not one but multiple controllers interconnected in a specific way. If every single controller adopts the scheme that you presented, will you be concerned about the aggregated latency, especially if inputs going through a cascade of controllers? Do you find this feasible? Would this scheme be feasible for deployment in a kind of a network of complex controllers situation?
So the short answer is yes. And in fact, the original name for this was Byzantine fault tolerance, which was getting at exactly that scenario. What I will say is that this is just now starting to get out of the research phase. We really haven't seen this concept deployed in commercial operational systems at the scale and complexity that you're discussing.
Right.
But the early indications are that it scales exceedingly well, right? So long as you can keep one of those controllers sufficiently behind the other ones, that delay is what breaks you out of that cascading Byzantine fault. Does that answer your question? Sort of?
Yes.
Okay.
A really nice talk, very interesting topic. So my question is, how do you determine the output from which controller you have to take? That's my first question.
Okay.
And my second question is, will there be a scenario sometimes that the crash gets delayed? That means it doesn't crash fast, and the attacker has control over one of the controller, and can he inject some malicious activity on the system or something like that?
So maybe. Let me go back to your first question. Restate your first question again.
So my first question was, like how do you choose the output out of the three, C0, C1, and C2? So
in the short answer is it doesn't really matter. And it doesn't really matter because you're not really trying to figure out what bad traffic looks like compared to good traffic. Essentially, by making the controllers brittle and having them crash on a sufficient anomaly, i.e. a malicious message, the crash of the system happens as a result of the brittleness of those controllers. And the crash also is the canary that tells you that something bad happened, that there's a malicious message on the line. So the only thing that matters is that you keep one of the controllers on a delay to keep it safe and clean. Otherwise, what's not pictured in that diagram that would be in a real operational commercial setting is another controller that it would be out of band that is monitoring for the crash and then sending the messages to the controllers to either reboot and recover. So that one's not showed, it's sort of implicit in the diagram. But so long as you have that, it doesn't really matter because of the race condition, if you will, that exists. Under normal operation with non-malicious traffic, controller 1 and controller 2 are going to be feeding you output. Controller 3 is always going to be behind, so the traffic is likely always going to be dropped. Controller 3 is only going to be executing the messages if controller 0 and controller 1 are not present. Does that make sense?
Yeah, so you have the priority
Yep.
for 0, 1, 2. Okay.
Yep,
Okay.
yep.
Got it.
Yeah, it's just without any loss of generality, we're putting them up and calling the delay queue on the bottom. To answer your other question is exactly the type of scenario that we're trying to prevent, right? So if an attacker or an adversary can actually slip a message in that is able to compromise both C0 and C1, that essentially foils the approach. So the presumption in our approach, one of the initial assumptions, is that we can make those controllers brittle enough so that any malicious message that compromises one will crash the other ones effectively immediately. It also presumes that the diversification of those controllers is sufficient, that there's not a fixed point in the code that is exploitable by the same piece of code across all the controllers, because that would give you a common mode failure. So if during the diversification there was a large swath of code that was left untouched, obviously an attacker, if they found enough ROP gadgets or they found enough exploitable material in the part that was not moved across all those components, you'd still have a common mode failure. So those are the assumptions going in, is that you are sufficiently diversified and that you are sufficiently brittle. So does
So
that
you have
answer?
a detection system and then you switch to
The detection system is essentially just detecting that there was a crash. Right,
okay.
so you don't actually need, this actually precludes, it's actually a lot simpler than a lot of folks initially observe it to be, because you don't need an intrusion detection system, you don't need anything. You're essentially using the crashed component as the canary that tells you that something bad happened. And then you don't even really care what bad thing happened, because the assumption is that it was trapped in that delay queue, and that you're going to save it off, or you're going to prevent that bad message from getting in there. You don't even necessarily need to care what it is. You just want to keep that third one clean.
Okay.
Is that,
Yeah.
okay.
Yeah, thank you so much.
So I want to be the devil's advocate a little bit longer. So in our experience securing the drone, the UAV controllers, our experience actually shows that if you provide some kind of a garbage or input, it is possible that there is no crash. So meaning that garbage in, garbage out, but it will keep doing that.
Right.
So the crash, right? Because the event of a crash is critical.
Yes.
Somehow our experience kind of indicates that malicious input does not necessarily lead to a crash.
Correct.
Yeah. So that. Yeah.
So let me go back to this one, right? So the scenario that you're describing, which I sort of refer to as sort of the most nefarious, the worst of all possible exploits, which is there's an exploit that doesn't cause a crash, but it does cause some unintended behavior. I referred to it as a low, slow sensor drift, where you're not going to crash the system, but you're just going to slightly perturb the sensor reading. That's not the only way. That's not the only exploit there. But the defense against that is to actually employ some sort of out-of-band simulator that allows you to essentially throw the flag and call a crash even if there wasn't a physical crash, right? And you're enabled to do that only if you have some out-of-band thing that tells you the difference between what normal and what your sensor readings say. So that's the need for this simulator.
In fact, I was expecting you to mention Blue Box, because that is.
I'll mention Blue Box because that is a Purdue effort. So since we're at Purdue, we can talk about Blue Box because Blue Box does exactly that.
Thank
Did I mention it's called Blue Box?
Thank you.
Yeah. Yeah, go ahead. Okay. You and then in the back.
Sorry. All right. So I have 3 questions, and essentially the first one is somehow is the same as Donnie asked earlier. Like, how could you guarantee this fast crash? I mean, I think in one extreme scenario, you just put assert and panic into each instruction. Like, as long as you see some anomalies, you just crash.
Yep.
So, but I don't think that's the way to do this controller programming. Second question is like how fast you need to do the packet filtering or this message filtering. I think it depends on like how many features you need to fingerprint a malicious message. So if you have like 8-bit message, then you probably only need like a limited number of memory to memorize everything.
Right.
But meanwhile, if you think about like denial of service attack in network security, if you have to filter like a million of different IP addresses, you probably need to build a Bloom filter, like, you know, to do something crazy.
Yep.
So I wonder like how fast do you need to do this like malicious message filtering? So that's the second question.
How fast or how
how-
many do you need to remember?
Yes,
Yeah.
pretty much the same. The last question is, you mentioned these out-of-band simulators. Does that mean like you need your controller to be equipped with some high-end like, you know, CPU or MCU? Because like, I don't think you are able to do the simulation on the controller itself, right?
No, you wouldn't want to do the simulation on the. You could, but I
You-
don't
you
think
can, you can.
You can, but you don't necessarily need to, right? So most of the implementations to date of an out-of-band simulator are literally out of band from the controller. It could be even as simple as like a Raspberry Pi that contains a comparator that is going to run it past either a
Pixhawk,
lookup
whatever
filter.
it
Yeah,
should work.
yeah.
Okay,
I'll refer you to Blue Box.
there we go.
But it could be
it
it
works.
could be as simple and naive as a lookup table, or a linear extrapolation of position or something like that, and then you have a comparator of the output that is coming from your, or the input that is coming from your sensor, and what the predicted value from your simulator is, and when there's a large enough
I see.
discrepancy, you call that a virtual fault, and even if
see.
you didn't see a crash, you call it a crash and you reboot and recover.
Yeah, I was thinking about, for example, ARM big, little. Like you have Cortex-M, you have Cortex-A on the SoC at the same time. You probably can run the simulation on the Cortex-A, meanwhile Cortex-M is doing the controller job.
Yep.
So,
And even though those are the same, they're big and little, that does give you a little bit of diversity too. Your second question about
Like,
like
yeah.
how many do you need to remember?
yeah,
Again, that's another one that probably falls into the system engineering category. It's going to depend on the system, and it's also going to depend on your risk tolerance, right? So it's basically how many unique messages would you want the adversary to have to come up with in a row to be able to denial of service you, right? If 10 is sufficient, then just remember 10, right? If you need 10,000, then you need to remember 10,000 messages that you want to blacklist. And then you could put those in essentially a ring buffer, so that like once you remember 1,000, you forget and you just fill up the queue as you go. So you're only going to remember the most recent 1,000. It's going to be whatever works for your particular system. So unfortunately, there's not a cut and dried answer for that one.
but like it can be tricky because you really need fast packet filtering.
You do need fast packet filtering, so that one will require you to have some sort of interrupt or some sort of man in the
I
middle
see.
on the bus. You can do that man in the middle on the bus, that shim in software. You can also do it in hardware.
I see.
So there are research efforts underway that will, for PLCs and industrial control systems, for those types of controllers, you could actually have a hardware shim that would essentially piggyback. There also, if that's either unpalatable or unfeasible, there's virtualized software shims that you could do.
I see. Thank you.
There's work in both of those areas. Yes.
Yeah, particularly you mentioned about the cars. If the engine control unit dies, of course nowadays the power steering unit and even the accelerator, everything is sensor controlled.
Yep.
Thanks God they haven't gone to the braking system, because if that one was the sensor, it would be difficult. But what happens if you are at a turn or you are changing lanes and then your engine control unit dies for whatever reason?
This will never protect you against purely mechanical failure, right? If the engine control system goes down or the engine goes down, that's like, this will never protect you from abject failure like that. The state of the system, so whether you're in a turn or whether you're braking or whether you're accelerating, won't really matter because the inertia in the system will still be the same, and you'll be able, if you're able to absorb the fault in the inertia of the system, it won't matter what specific instantaneous state you're in. Does that make sense?
I'm telling you, if you are turning and you have the momentum, it's out of your control because you
Right.
cannot turn if it's just sensor unit, sensor control, or don't care about the acceleration because the accelerator is not working. But I'm talking about turning, or right now, of course, it is mechanical system for braking, but the way that they control it is nowadays you basically, you say by Google whether there's a turn or something, but if somebody
Sure.
changing turns, lanes, or you're turning, you are not in a tunnel or whatever. Basically,
Right.
you lose the engine control unit. Basically, a lot of things are controlled by the engine. When it dies, you lose a lot of control. So
You do lose control, but the whole premise of the concept is that you want to shrink the window of the uncontrolled time down to small enough where the inertia of the system can actually absorb that fault. In the original example that I gave of like the braking on a car, if it's straight line braking, you probably won't ever notice. If you're braking while you're turning, the car may deviate from its original intended target, but should be able to recover. So it's not going to go exactly where you had planned for it to go, but because of the inertia of the system, it should be able to absorb it and get you back on track without a large deviation. And this is where it becomes yet another systems engineering problem, where I would kick it to the system engineering community to essentially give you that safety envelope and create your window, the size of that message queue, such that you never deviate from the safety envelope of either plus or minus, several feet.
no, I mean, if there are some other people next to you, it is when you are just in
Yep.
the middle of nowhere, that's okay. But if you have people just driving with you 60 miles per hour, 70, 80, whatever,
Right.
yeah, so that's going to be a different story. That
The theoretical, so just to give you some specific numbers, we're usually talking in milliseconds, 20 milliseconds up to about 200 milliseconds. So a fifth of a second all the way down to 10, 20 milliseconds is really all that is required to be able to recover some of these controllers. So in that period of time, even if you're going 60 miles an hour and you're in the middle of a turn and you're braking, the inertia of the system is still going to be able to absorb most of the fault. And while you may not be exactly where your intended steering target would have been, you're not going to be that far off to be so far out of your lane that it's going to be unsafe. But this is the kind of question that I think falls into that systems engineering of when you're going to actually put this on a very specific system with very specific safety considerations and tolerances, you need to figure out what that envelope looks like. Yeah. Thanks for asking questions, by the way. Like, thanks for not just being like silent.
Okay, the question is regarding, you're mentioning about the fast reboot.
Yep.
So what if I have a persistent threat?
If you have a persistent threat, all bets are off, right? So another thing that this approach is not going to protect you against is if there's some sort of hardware Trojan that is baked into the supply chain that is always there and was there before you implemented this concept. This will provide you a little bit of resilience to it, but that supply chain vulnerability in the hardware is akin to a common mode failure, right? If it's in every single one of the chips, all bets are off. Yeah.
So when it comes to like comparing against the out-of-band sensor, you're comparing within a range of tolerance, correct?
Yep.
What if an attacker brings in your sensor information to while maintaining the range of tolerance to the point where you're getting to a physical site damage? For example, reducing the timings in an engine so that you're running leaner and then the engine will more likely fail faster. How will the system handle that kind of an attack?
So it will The short answer is it will handle it however it handles it. This one is mostly focused on preventing unsafe behavior of the physical system, right? So it's not as focused on preventing wear and tear on the individual components, right? If that makes sense. So if you have an attack, say, which I think is the one that you're describing, let me know if I'm putting words in your mouth, but I think the attack you're describing is some sort of attack that would not take you out of the safety envelope, but would cause extra wear and tear on the components and maybe cause them to fail faster or use more fuel or be more costly. Is that right?
More or less, yeah.
So long as those attacks, so if those attacks did not cause the physical system to behave in an unsafe manner in the physical world, this approach is going to let them continue, right? If those approaches do manifest themselves as unsafe behavior of the physical system, this one will catch it. And this again is where I would kick it to more of a system engineering exercise, because you could actually bake that in, you could bake those in as additional requirements. So if you know, for example, that going back to the car exercise, if additional RPM is going to cause additional wear and tear on the car, you may be able to bake that into your message queue to keep that at a minimum.
I was mostly talking about, like, for example, for your air-fuel ratio. If you run leaner, you're more likely to get to the point where your car will just die midway, and you won't be detected for like a long time, but it will double the costs.
Yep.
Yeah.
Yeah. So I think that is a consideration that you could bake in when you're trying to calculate the message queue and the safety envelope that you want to be able to operate the system in.
Okay.
So you could extend the research to not just look at the unsafe conditions of the physical system, but also anything that would contribute to long-term maintenance and wear and tear and additional costs.
Thank you.
So.
Any more questions? No? Let's thank the speaker again.
All right. Thank you.